Hello everyone, welcome to the video. So in this video today we have a distinguished guest with us, Professor Tejinder Singh of TIFR, Tata Institute of Fundamental Research, Mumbai. So he has been doing some great work on the foundations of quantum mechanics and quantum gravity and unification. He's affiliated with the Department of Astrophysics and Cosmology of TIFR, and I recently listened to his talk on one of his latest works about extra time dimensions and a new theory of space-time. So we'll be talking with him about this and a lot more. Especially, we'll be covering many important points in the foundations of quantum mechanics, quantum gravity, and many more. So today we have a distinguished theoretical physicist with us today, and I think this is going to be a very insightful discussion. So first of all, thank you so much, sir, for your time and for agreeing to be interviewed. We're really grateful to you for your time. So
Thank you.
yeah, so my first question to you, sir, would be, what got you interested in physics? Like, if you could go back to your childhood, and broadly, what changes have you seen in the physics landscape from your childhood days to today?
Yeah, thank you. Thank you for having me. Um, yeah, I can recall one or two incidents during my childhood days which were very interesting. One was not directly related to physics or science, but a strong perception of and response to natural beauty. I mean, we were living, my parents and me and my siblings, we were living in Dehradun, in near in Clement Town, which is very beautiful. Used to be very beautiful part of the lower Himalayan hills, and that natural beauty at the age of around 5 or 6, it affected me very strongly. So maybe some sense of this elegance around us in the universe was built from there. Then 1969, I vividly remember being struck by the news that man has landed on the moon. It had a big impact on me. I knew that this was something not very usual. I was only 7 years old, but it affected me in a big way. Then the other major piece of information I can remember is when I was in grade 12th. There used to be this magazine called Science Today, which no longer exists, Indian Science Magazine. And there I understood that the stars that we see in the sky, they are part of only our own galaxy, the Milky Way, and there are other stellar bodies known as other galaxies which are outside the Milky Way. Somehow that had a big, again, impact on me that the universe is much bigger than what we see in the stars in the sky at night. And from there on, learning a little bit at the popular level that the universe, quote unquote, began with the Big Bang. We don't know if it is true, but at least that was and still is the dominant model. And that got me interested in um wanting to understand uh, how the universe began and what was there before the beginning. And I learned in a hazy way that this has something to do with knowing, trying to find out a quantum theory of gravity. So that sort of became a motive, but it was all in the background. I mean, as my parents and my friends would suggest, I wanted to study engineering like most other people were doing at that time. So I went to engineering college and joined for chemical engineering. It was a 5 year course. But after the first 2 years, when I was introduced to Feynman lectures in physics, I realized this is not what I want to do. I want to do physics. Those questions came back to me. What was there before the Big Bang? How does one uh, quantize gravity? Whatever that meant to me at that time. So that in the third year at the engineering college, I switched to physics. So nothing very profound, but just a general interest and curiosity towards understanding and solving problems of the universe. So that's that. That would be 1986. No, no, sorry, 1981. So since then, I did a bachelor's and master's in physics and so on. And your second part of your question, change in the landscape of physics from those days to now. So I can only comment on the part of theoretical physics which we might call fundamental physics, foundations of quantum mechanics, the standard model, foundations of the standard model of particle physics, our understanding of quantum gravity. So I learned the traditional way, all these things, and did, let's say, what we can call modest mainstream research. But over the years, I have learned that in these fields, we are stuck. We have not understood or solved the foundational problems of quantum mechanics. Over the last 100 years, those problems are still with us. And I think they are very central to why we are not being able to make progress. We have to address quantum foundations before we can make progress in quantizing gravity and before we can unify gravity with the standard model of particle physics, before we can understand why the standard model has, say, 25 or 26 dimensionless fundamental constants, I personally feel all that requires a rethink at the quantum foundational level, and that is what has guided my research. And so, to come back to your question, what has changed in the physics landscape? That after the mid 70s, when the standard model was already in place and model of particle physics, general relativity was firmly established by then, apart from, say, the discovery of gravitational waves, which inevitably came. Uh, we are stuck. So the landscape is stuck. Uh, we need something radical on the theoretical side, not on the experimental side, on the theory side. And that's what is guiding my research along with my collaborators.
Thank you so much, sir, for the insightful answer. So, yeah, I would like to now, next question, I would like to go a bit into the theory versus experiment debate. So, a lot of people have this, I should say, have this feeling that experiments has not developed to the level that we can verify the theoretical claims being made by the abstract theories like string theory and all. But like, what is your view on this? Like the theory versus experiment. Are we lacking on the theoretical side more and the experimental side more? And how do you think we should physicists should resolve this apparent gap between theory and experiment?
Yeah, so my view is that theory is way behind experiment for the following reason. The experiments have already given us a lot of data. Even something as simple as why does the universe appear to have one dimension of time and three of space, and why their signature is opposite. This is data. This is data. We have to explain it. More specifically, if we go to particle physics, we have more than 20 dimensionless fundamental constants, like the low energy limit of the fine structure constant. Why is it 1 by 137? Mass ratios, why the muon is 200 times heavier than the electron, and why the cosmological constant has the value it does, or is it zero? This is all data. What is the nature of dark matter? So experimentalists have done a great job. We theorists have fallen behind. And the reason for that, again, I believe, is not addressing foundational questions in physics, the quantum measurement problem, the quantum non-locality problem, the problem of time in quantum theory. My own work suggests that when you try to start addressing these questions, you make progress towards quantum gravity and unification.
So, like, since you mentioned this arbitrary parameters in the standard model and some numbers we don't understand. Like, I was reading your blog. You wrote a blog about the mass ratios, the apparently
Mm.
strange looking mass ratios. So, I have. done a little like little bit of work on the modular group and the use of modular forms to study neutrino oscillations, like why do the neutrino oscillations happen in that those particular things. So and although I'm not very familiar with the mass ratios, but I have seen many examples of if we can find a general mathematical structure, then that can explain a lot of things automatically that appears very arbitrary to us, like at first glance.
Hmm.
So
Yeah.
then my question would be, what do you think, like about this? Like if we can find a general mathematical structure, then will all of physics, or maybe not all of physics, but will much of this arbitrariness in physics be resolved automatically in that sense, and in a general perspective, not just in one or two examples, but
Yeah. So again, I would come back to first addressing key questions in quantum theory. That's where we start. That guides us to what general structures we need. And the central problem there, in my view, is the so-called problem of time in quantum theory. And what do I mean by that? The universe is dominated by classical macroscopic bodies like stars and galaxies. They coexist with the classical space-time. So in my picture, no classical bodies, no classical space-time. No classical space-time, no classical bodies. These two things go together. But we use a classical time parameter in quantum theory, which is only possible when the universe is dominated by macroscopic classical bodies. On the other hand, though, these classical objects are a limiting case of quantum theory. So it looks like quantum theory depends on its own limit. And this is true at all energy scales, including the energy scale today. If you were to imagine that you take all stars and galaxies and split all their particles apart into their fundamental structure, electrons, quarks, neutrinos, go down to their microscopic quantum structure, and imagine for a moment that the universe only consists of disjoint elementary particles and there are no stars and galaxies. Today's universe, low energy universe, I can even do a thought experiment like that. Then it can be argued that in such a universe, you will not have a classical space-time manifold which we can label by real number valued points. Um, but I still need to be able to describe the dynamics of such particles. I don't have space-time, I don't have a classical time parameter. So if everything is quantum mechanical, I don't have classical space-time, even at low energies. And so that tells us that this is a clue how to redo quantum theory, how to reformulate quantum theory without referring to classical time. So let's imagine that there is a way to describe the low energy universe without space-time being labeled by real numbers. And I want to put particles in such a universe and then do quantum theory for them. Then when many of these particles get entangled in different subsets, they will form classical bodies like stars and galaxies. And then classical space-time will emerge. And those bodies, those objects which are still microscopic, I can do quantum theory for them in the emergent space-time. So space-time emerges along with classical bodies after entanglement of quantum systems. But the more fundamental universe must be described by using a different version, a different structure of space-time, which is not labeled by real numbers. So that was the guiding point. And for various reasons, we homed him in what are known as division algebras, the natural generalizations of real numbers. to complex numbers, quaternions, and octonions, the only four number systems for which division is defined, namely, if A times B is 0, then at least A or B, one of them should be 0. So instead of labeling space-time by points, we label it by quaternions and then generalize to octonions when we want to include internal space-time symmetries of the standard model of particle physics. So each point is replaced, let's say, by a quaternion, or more precisely by what is known as a split biquaternion, which takes care of chiral fermions. So in this new structure of space-time, when you try to place particles, you cannot place fermions of arbitrary properties in a space-time labeled by quaternions. The properties of the fermions themselves get restricted. And that is where it seems that the apparently arbitrary dimensionless fundamental constants emerge because the structure of spacetime is now not that of real number points. There is a more non-trivial structure which dictates what kind of particles you can put there. Spacetime tells matter what to be. Not only does spacetime tell matter how to move, it also tells matter what to be. While it's also true that matter curves space-time. Now the curving is of a non-trivial nature. It's not a Riemannian geometry. It's a generalization of Riemannian geometry to non-commutative geometry. And then if you include the other forces, a generalization to non-associative geometries. This is ongoing research. But I hope you get the picture. We don't do quantum theory on a classical space-time background. We do quantum theory on a quaternion or octonion space-time background. And that is what seems to remove arbitrariness in values of parameters, why there are four forces, why space-time has 3+1 dimensions. We seem to make some progress towards understanding these questions. Still ongoing research, but it looks promising. And what is very important to remember that this has to be done at low energies also, like the universe in which we live. So there are two aspects to quantum gravity, the quantum nature of the gravitational field and the non-classical nature of the space-time manifold. Quantum gravity is not only about the gravitational field or the metric, it is also about the space-time. Whereas the other quantum forces like QED, quantum electrodynamics, or quantum chromodynamics, or the weak interaction, they are only about the field's quantization itself. They are not about space-time. They take a space-time as given, fairly so. You cannot do that when you try to quantize gravity. You cannot take space-time as a given. You have to quantize space-time manifold also, which means replace it by a non-real number system like the quaternions.
Okay, thank you so much, sir. Now, I would like to talk a bit about your paper, time-like extra dimensions, quantum non-locality, spin, and serials unbound. So in
Mhm,
this way, in this paper also you suggest that there is a six-dimensional space-time and
mhm,
which is actually an overlap of two four-dimensional space-times. So
mhm,
my question would be, one of them I gather is the space-time we're familiar with three space and one time dimension. And so what about the other space-time? And specifically, when you say time-like dimensions, then are these time-like dimensions the same as the space-like? What is the difference between the time-like and space-like dimensions?
mhm.
That is the question.
Yes. So we could start by asking why six-dimensional space-time? Where did it come from? So in this, when we were generalizing space-time by removing real numbers and replacing it by quaternions, we noticed one very curious thing, that if we want to have both left-handed and right-handed fermions, which is how they are, only left-handed fermions take part in the weak interaction. So they come with this so-called specific chirality. There's a left-handed electron and there's a right-handed electron. When we want to place both left-handed and right-handed fermions on this quaternionic spacetime, we realized we cannot do with 4 dimensions. So we have to have what are called split biquaternions, which is a doubling of quaternions in a specific way. And those are naturally associated with 6 dimensional spacetimes, with 3 space and 3 times. That's how we were sort of forced to have a 6 dimensional. If you want to describe fermions and spacetime using division algebras, and if you want the fermions to be chiral, you are forced to a 6D spacetime, even if you see only 4D. But we know from the history of physics, what we see is not always the same as what actually is. We push the boundary. So the 6D spacetime after a early symmetry breaking at the electroweak symmetry breaking in the very early universe divides into 2 overlapping 4D spacetimes. The one that we are familiar with, 3 space and 1 time. Another one that we are not familiar with, 3 times and 1 space, and 1 time and 1 space overlapping. The other spacetime has compact dimensions much smaller than ours. They are driven by the scale of the weak force, and the space-time curvature of the other space-time is given by the weak force. The weak force is the left-handed analog of gravitation. Our space-time is curved by gravity, the other space-time is curved by the weak force. And those dimensions are very tiny. That's why we don't see those compact, tiny time dimensions, which are of the order of 10 to the power minus 26 seconds. They are there, but they are too tiny, but not beyond detection. They are not Planck length, Planck time scale. Planck times 10 to the minus 43 seconds. This is the weak time scale, around 10 to the minus 26 seconds. And what is the difference between space and time? I would say only the signature. Time coordinates are like space coordinates, but they come with the opposite signature. And none of these times is the time that flows or keeps track of past, present, and future. That's a different time. It's an extrinsic new time parameter coming from non-commutative geometry, which in the classical world we identify with one of these times t1. So our universe has only one of these 3 times, our 4D universe. That time gets identified with the so-called Cohn's time, that flowing time parameter. But as such, the time coordinates do not flow. They have the same status as space. And you could think of the block universe picture like if you draw a 2D space-time diagram, with x on the horizontal axis and t on the vertical, and draw a particle trajectory on this space-time. We don't say that the particle is at x1 at time t1 and at x2 at time t2, etc. We say that the entire trajectory is a given. The trajectory is there, it pre-exists, like in the principle of least action, where you solve for the entire trajectory by extremizing the action. We are flowing through the extrinsic time parameter so as to be at x1 t1 at an extrinsic time tau1 and at x2 t2 at an extrinsic time tau2. But the entire trajectory is given. The universe is already given. Its history. In that picture, it is easier to understand time coordinates as being on par with the space coordinates.
The 6D space-time is an overlap of two 4D space-time. So there are one space and one time dimensions are overlapping, like are common to both the space-time. So I gather that the time we are familiar with is this overlapping time, right?
Yes, yes.
Okay.
But
So
what we have to be careful about is what we call the space-time metric. The space-time metric in our 4D space-time is very different from the space-time metric in the other 4D space-time. And distances in that space-time are much smaller than ours, distances and time intervals. So even on this overlapping time direction, they are setting two metrics. Our metric, according to which the universe is about 10 or 13, 14 billion years old. The other metric, in which the universe is only 10 to the power minus 26 seconds old. So even on this shared direction, the extent of time is different in the two universes.
okay, that's a very crucial point. Now, I would like to ask you, weak force is causes the curvature of that space-time, the other 4D space-time, and gravity for us. So, where do the other two forces, fundamental forces, as we know so far, the strong force and the electromagnetism, how do they fit into this
Yeah.
picture?
Strong and electromagnetic force are the internal symmetry spaces of the second 4D spacetime, and there are correspondingly two new predicted forces which are internal symmetry spaces of our spacetime. That is dark electromagnetism, which is the correspondence to normal electromagnetism, and strong gravity, which is the correspondence to the strong force. So we are predicting a total of six forces. And apart the weak force and gravity are space-time geometries. The other four forces are internal symmetries, and for describing them, we need octonions. For weak and gravity, we need only quaternions. But when we want to add internal symmetry spaces and bring in the quarks, then we need the octonions. So it's very beautiful. Real numbers for the classical picture, the complex numbers somehow go for a ride. They are important in quantum mechanics and for the two-dimensional plane. But for our space-time, quaternions and split by quaternions 4D and 6D, and for including gauge forces, the octonions. So it's nice. Real, complex, quaternion, octonions, all are getting used and no more. It's as if the universe is built very intelligently using division algebras.
That reminds me. Now, this might be a very stupid question, but personally, do this almost it's almost as if God is a mathematician, if you think about it. The way
Um, all said and done, God or the agency that makes the universe is a mathematician. The universe is a one particular mathematical realization of the very vast arena of mathematics. I believe that the physical and the mathematical universe are one and the same, with the physical universe being one particular realization of the mathematics. Deep down, we cannot describe physical systems without mathematics. It reduces to mathematics. Like we say that a fundamental universe is made up of atoms of space-time matter. The only way to define those atoms of space-time matter is to appeal to the octonions or to appeal to matrices which are dynamical degrees of freedom and write an action principle for these atoms of space-time matter. And then that is it. Rest is all language or visualization, but what carries the day is mathematics. Yes.
Yeah, and I mean, there was a very famous paper by Eugene Wigner, what he called the unreasonable effectiveness of mathematics in the physical sciences. So if you think about it, a lot of mathematics theories that were developed way back without any direct application in mind, like linear algebra or even group theory, but ultimately they turned out to be the framework required to study symmetries, like for group theory. And if we talk about the canonical formulation of quantum mechanics, it's all based on linear algebra. So it's
Hmm.
kind of very astonishing, and I totally agree with you. Like I recently posted a blog on my website also, that mathematics, the future of physics, and I also personally believe like it's a kind of that the physical universe is a kind of a subspace of a much more general mathematical space, and
Hmm.
it's absolutely fundamental. It's not just a language. I mean, uh, at the fundamental level, if we talk about mathematics. So my next question is following this. I read your paper, and although I couldn't understand all of it because it's a bit advanced for my knowledge, but there are like when we define a quaternion, it's like it has one real component. Like it's like a plus ib plus jc plus kd. So where a is the real part and b c d are the imaginary parts, and where I j k, they are just like I square equals j square equals k square equals minus 1. And for the split quaternions, we have this is equal to plus 1. The I square j square k square, they equal to plus 1. And I understand like that beautifully gives us the, if we take the norm of the split biquaternion, like a plus ib, where a is itself a quaternion, b is another quaternion, but this I squared is plus 1, so that's a split biquaternion. Then we get this metric, that signature that we want, the opposite signs for space and time. Now, my question is, if I'm not much mistaken, we took only the imaginary parts to be the six to to make the six-dimensional space-time. Like, so why the imaginary parts and why not the real parts?
Yeah, that's a very good question. My present understanding is that the real part goes for the Higgs boson. One real part for one Higgs, the other real part for a second Higgs. So we are predicting a second Higgs in the theory, which, if our theory is correct, it should be looked for and found. So that's the picture. Somehow the imaginary directions are going for making a 6D space-time, and the two real directions are going for making the Higgs. That's my picture right now.
So what is the, what does the second Higgs do? Or
Yes, yes. The standard model Higgs gives masses to particles. The second Higgs gives electric charges to particles. So unlike in conventional theory, in our work before the electroweak symmetry breaking, we only talk of a quantity which is a combination of electric charge and mass. E times root m, electric charge times square root of mass. And after symmetry breaking, one Higgs assigns masses to particles, other Higgs assigns electric charges to particles. E root m splits into E n root m. Yes.
that's really beautiful, because now we are not even assuming charts. That also comes from the, automatically
Yes.
comes from the framework. That
Yes.
is so from what I understand, this framework has a lot of predictive power also, not just explaining the data, but also makes a lot of prediction, which I think makes it testable and falsifiable, and which are the
Yes.
hallmarks of a scientific theory. So
Yeah, it
it's
is falsifiable, definitely. And our goal is that we will not put anything by hand. The fundamental action principle has three constants: Planck length, Planck time, and Planck action, h bar, the quantum of action. So Planck length, Planck time, and h bar. Everything should be written in these units. The action should be made dimensionless by dividing by h bar. And on the right-hand side in the action principle, quantities of length dimension should be scaled by Planck length. Quantities of time dimension should be scaled by Planck time. So the action itself is dimensionless, and this is it. On a quaternionic or octonionic space, octonionic if you want to include internal symmetries, on a quaternionic or octonionic space, write the so-called trace dynamics action for metrics valued degrees of freedom. That's it. Now that's it. From here, derive, because of the properties of octonions and quaternions, six forces. Yes, and you need a gauge symmetry group. I forgot to mention that. You have to start with a presumed gauge symmetry for the overall unified action principle. And that happens to be something known as E8 cross E8 for various reasons, because it gives us the world that we see. Now, this E8 cross E8 became very popular in the 1980s as one of the promising unified gauge groups of string theory. But then, for various reasons, it became less popular. It didn't seem to work. But we have revived E8 cross E8, and we have a different interpretation for how the symmetry breaking should take place. And again, quantum foundational questions are playing a very important role here. How did we land up with the quaternions and octonions? Because we wanted to remove classical space-time from quantum theory. And octonions and E8 have a very intimate connection. So that's how we have E8 cross E8 as the gauge symmetry group of the fundamental theory, and with space-time being replaced by octonionic space. So instead of having classical particles on a real number valued space-time and you quantize the particles, we have matrix valued degrees of freedom for particles on an octonionic space. And this is already a pre-quantum, pre-space-time theory from which what we know should emerge, and it looks promising.
Okay, now since you mentioned trace dynamics, I remember you mentioned trace dynamics to me when we were discussing once, and I don't really understand what that is. So if you could, and even for my audience, if you could in brief mention like what is trace dynamics and how
Yeah,
is
yeah.
the approach?
It's very simple to describe. I do classical mechanics with real numbers, position and momenta, Q and P, and we write an action principle for, let's say, a free particle using real numbers. Let's say half mv square is the kinetic energy. You make a Lagrangian and half mq dot square. You integrate it over time. That is your action principle. Here q is a real number. Suppose I say I want to do classical mechanics now with matrices. My q becomes a matrix. Yeah, it's not a real number, it's a matrix. So I take it's the time derivative of the matrix Q, Q dot, which means time differentiate all the entries in the matrix. Take a square of the matrix, the matrix polynomial. Q is a matrix, Q dot is a matrix, Q dot square is a matrix. I want to make an action principle, but I want my action as usual to be a scalar. Then I take a trace of Q dot square. That's a scalar because it's a trace. And I integrate it over time. So my action now is integral dt trace q dot square. That's where the name trace dynamics comes from. And what do I get? I can find the equation of motion by varying this with respect to the matrix Q. And you will get Newton's laws. You get Q double dot equals 0. Or if you have a potential term like Q square, you'll get Q double dot equals minus Q, the harmonic oscillator. So then one might say, what's the big deal? You're doing classical mechanics with points, or you're doing classical mechanics with matrices. What do you gain? Why do you do it? Interestingly, very interestingly, it turns out that for some very elegant reasons, this matrix value dynamics is not classical in the sense of Newtonian mechanics and special relativity. It is even more general than quantum theory. What's the reason for that? Suppose you have Q's and P's, which are matrices. Your position and moment are matrices, like in quantum theory, because you raise Q's and P's to operators. But now I'm now, so to say, doing classical Lagrangian dynamics, but my Q's and P's are not commuting. Their commutator is arbitrary because dynamical variables evolve according to equations of motion. The QP commutator is not subject to a constraint like quantum theory. QP commutator there is IH bar. In quantum theory, this commutator is Q, comma P commutator is IH. QP minus PQ is IH bar. Here, QP commutator is evolving dynamically. So that is what makes it trace dynamics a pre-quantum theory. And under certain emergent approximations, the QP commutator becomes IH bar. So quantum theory emerges from matrix valued Lagrangian dynamics. Let's not call it classical dynamics because that's confusing. It's a matrix valued Lagrangian dynamics patterned after classical dynamics, but which is more general than quantum theory. So what we do this matrix valued Lagrangian dynamics on an octonionic space. So it's very beautiful. Newtonian mechanics was real numbers on a classical spacetime, real number valued Q's and P's. General relativity made spacetime curved but kept it real number valued, and Q's and P's were still classical. Quantum theory made Q and P into matrices or operators, but kept the spacetime fixed at real number value. These are two different kinds of departures from Newtonian mechanics, which are in conflict with each other. As I explained in the beginning of the discussion, if you make Q's and P's into matrices, you cannot leave your space-time as real number value. There's a contradiction, there's a conflict. The only way to avoid that conflict is to remove the commutative nature of space-time and replace it by non-commuting numbers like quaternions. That's why trace dynamics on a non-commutating space made up of quaternions or octonions is a natural point of departure from quantum theory. If you were to bring Einstein and Schrodinger together, if they, let's say, had a thought experiment kind of discussion and a negotiation treaty, how should we proceed from Newton? I would say, please follow Adler and octonions. Do both together, curve space-time, but in a quantum way, because you are raising matter degrees of freedom to matrices. The curvature produced by matrices is not Riemannian geometry of classical space. So we are still doing Newtonian mechanics in the philosophy. You get what I'm saying?
Yeah, I got it, sir. But these matrices that we had, like we define the P or the Q as a matrix. So how do we determine the elements of the matrix? Or are these like diagonal matrices or?
No. They are not diagonal. The entries of these matrices are what are known as Grassmann numbers. Grassmann numbers are anti-commuting numbers, and the square of a Grassmann number is 0, if I remember it correctly. So, and fermions are described by matrices made up of odd grade Grassmann numbers, which don't commute with each other. Bosons are described by matrices made up of even grade Grassmann numbers which commute with each. This is same as in quantum field theory. This
Yeah.
language of Grassmann
Uh,
valued
I
matrix.
came across I actually came across Grassmann numbers when doing like when learning path integrals in quantum mechanics, like Feynman's approach.
Mhm. Yes. So trace dynamics is very close in spirit to quantum field theory. It's just that we don't impose the Heisenberg commutator QP equals IH, QP commutator equals IH bar. We don't impose it by hand from start. We let it emerge when we let the underlying commutator to be arbitrary. That brings a bonus. that quantum theory as well as the measurement process, collapse of the wave function, both can be tied together, unified in the trace dynamics language. So trace dynamics unifies the unitary evolution aspect and the reduction aspect of quantum theory. Schrodinger evolution as well as reductive wave function collapse during measurement, both are unified in trace dynamics. And trace dynamics is also the very natural language once you set up your space-time to be quaternions or octonions. They go very well with each other naturally.
Okay, sir. Sir, now I would like to talk a bit about the quantum foundation, especially the question of locality and
Hmm.
realism. So, like Bell's inequality and these kind of experiments have shown the violation of Bell's inequality. So that means local realism must not be true. So either localism is false or realism is false or both are false. I mean, of course, physicists would try to go with the approach that at least one of them is false because assuming both are false would be a lot, would demand a lot of radical changes. So, in your theory, in your paper, and also in your talk, you gave a very good example how these extra dimensions of time, time-like dimensions in your theory, they can actually take care of non-locality because if two events appear non-local in our 4D space-time, they can actually still be local in the entire 6D space-time. You gave a good example. So my question to you would be if you could briefly just illustrate that as briefly as possible to my viewers, and also why do you think like localism should be preserved and realism? I mean, localism should be preserved over realism, if I put it that way.
We can come to both. So let's first look at locality. Uh, what we are trying to ask is how do correlated quantum systems manage to influence each other outside the light cone? This is confirmed experimentally by Bell's inequalities being verified by experiments. Correlated quantum systems influence each other outside the light cone. So I'm not saying anything travels at the speed of faster than speed of light. I'm not using that language. But something happens. So that I use the word influence to, and that, to my mind, is certainly in contradiction with special relativity. It should not have happened, but it is happening. And there is something to be understood, even though there is no contradiction with experiment. I would say there is a contradiction with special relativity. How did this happen? So when we were from our particle physics unification studies, when we arrived at a 6D space-time, then we realized, oh, this can address the quantum non-locality puzzle because events might be local in the 6D space-time, but appear non-local in 4D if we project out the other two times, which are having to do with the second space-time. And what the second space-time curved by the weak force is doing is giving a, because the metric is very small, the distances are very small, it's giving a second channel for Alice and Bob to communicate with each other. There is a new particle associated with the fifth force, dark electromagnetism, we talked about, the dark photon. The dark photon is transmitting the influence locally, obeying special relativity through the second 4D spacetime. And Alice and Bob, even if light years apart in our 4D spacetime, are only about 10 to the minus 16 centimeter apart in from the other spacetime point of view. And the dark photon travels very quickly from Alice to Bob. But we don't know that the dark photon is doing this. So it looks like uh, non-local influences have happened in our space-time. But we call that the quantum wormhole, just to make it sound nice. There's a quantum wormhole connecting Alice and Bob, which is the second 4D space-time, through which transmission happens locally, traveling at the speed of light through the dark photon. Speed is not superluminal. Speed is speed of light, but distance is less. Distance is 10 to the minus 16 centimeter. Time taken is around 10 to the minus 26 seconds. So the influence is not instantaneous. It's just too very fast so as to appear instantaneous. But it takes time. It takes 10 to the minus 26 seconds. And if we had that kind of time sensitive technology, we would detect it that it is not instantaneous. Our current time sensitivity bounds around 10 to the minus 18 seconds. If we can push that to 10 to the minus 26, we will see something interesting.
No, I think the appeal of this theory is that it's not because it explains non-locality, but because it explains a lot of other things as well. And so,
Mm.
and if we have to accept a theory, we have to accept all its predictions. It's not like let me accept this part of the theory, but not this part. So it's a very unifying picture, which not only explains non-locality, but it explains almost everything, even makes new predictions as well. So, I mean, I think this is the future of physics. Future of this theoretical physics could be interesting, especially if we can push our experimental limits a little bit, like you said, to that time scale. And if we could, definitely that would be a very definitive evidence we would be getting. So, and now, sir, let me ask a very kind of imaginative.
Sorry, sorry
Yeah,
to
yeah.
interject you. So
Yes,
look,
yes.
quite a few people are now working with octonions, trying to understand their role in particle physics, in gravity, and in space-time. Lesser so trace dynamics, but I think if more attention is focused to octonions and trace dynamics, we will make progress. And that is what I call a break from standard quantum field theory, normal approaches. And you asked about the change of the physics landscape. So I feel we are in good times again. We have to look at these kind of new theoretical ideas, relevance of octonions, relevance of trace dynamics. It is in this sense that theory was behind. Theory was lacking in new ideas. And we have to remember that these new ideas have sprung from addressing foundational problems of quantum theory. You address those problems, you seem to be able to help particle physics and quantum gravity, which is gratifying, it's encouraging, and it gives you a framework where you can explain data. And very importantly, this is not happening at the Planck scale. What we are saying is to explain the physics, the world that we see already at low energies. We need new physics ideas already at low energies. So in that sense, theory is behind. I'm talking low energy physics, low energy fine structure constant, ratio of the muon mass to the electron. None of this has to do with very high energy physics or Planck scale where experiments have not been done. But respectful addressing of foundational problems of quantum theory is very rewarding.
Absolutely. So now the question that I was going to ask is it's a very speculative question, but do you think if physics developed a bit differently, I mean, maybe suppose let's say quantum theory came before special relativity or something like this, like then would it be possible that we would have like reached at a very different picture, or if not very different picture, then at least we would have reached I mean the this landscape or this evolution of physics, the theoretical physics would have been very different from what it has been in our history.
Yeah, yes. So just take, for example, a situation like if Newton had discovered trace dynamics, if Newton knew about octonions, he could have done all this right then. He would predict new forces, he would come up with particle physics, he would come up with quantum theory. So we have not departed from the philosophy of Newton. Deterministic evolution described by mechanics. We are still doing the same Newtonian philosophy, but with new mathematical discoveries, Riemannian geometry, non-commutative geometry, division algebras, quaternions, octonions, trace dynamics, all this has come post-Newton. So now, suppose Even in the start of the 20th century, we had a better understanding of octonions, and we already had trace dynamics has its beginnings actually from that time. From work of Pascal Jordan, there is some evidence already of he was thinking of such things. So again, if trace dynamics had been discovered in the early 20th century, uh, things might have been different. But we have to remember theoretical physics is driven by experiment. Quantum mechanics, as it developed, was describing the current experimental situation of that time. And fair enough, we should not say you did not do things rightly, that's why we are in a soup. No, they did beautiful things. They developed quantum field theories, they developed gauge theories, they developed the standard model, which is consistent with all data. But what, in my view, got neglected is quantum foundations. They went outside the mainstream. What we got the shut up and calculate culture, and emphasizing or exploring quantum foundations will not help particle physics and general relativity. That is where I disagree. Those problems should have been given their due regard. There are big gaps in our understanding of quantum theory, and that is what I believe held back progress in unification and quantum gravity, and that's what we are grappling with now. So, if this movement happens, study quantum foundations to make progress in particle physics and quantum gravity, that movement might bring about a change in the next 10, 20 years. And I think India and young Indian students can play a role in that, an important role. Do not just look elsewhere. What's happening there? What is the trend? What is their philosophy? No. Think for yourself. Try to break from tradition. Work on what you think is important. So decide for yourself. Are quantum foundations important or not? In my own research, in my own development, it took me 20 years to even realize that there are these kind of problems. That measurement problem is a problem. I appreciated when I was 40 years old. Till then, it was not a problem. I was with what others used to say, uh, quantum foundations. He works on quantum foundations. That was a derogatory remark. To work on quantum foundations was to get oneself into trouble from the career point of view. And maybe it is still like that, but we have to fight. We have to, like, I would give an example like Kepler. He overturned 2000 years of belief system that orbits are circles. He found from 4 years of research on the orbit of Mars that it is not a circle, it's an ellipse. That's a break. That's courage. Takes courage to say that for 2000 years you said it's a circle, but I'm finding it's not a circle. It departs from the circle. So that way, if you think quantum foundational problems are important, you have to fight. You have to have that courage. You cannot say that, no, my career will be ruined. Do you want to save your career or do you want to be Kepler? Gary Kepler could have saved his career by producing a circle, but such radical breaks is what make progress. So I would like to hope that India is one such place where young minds, it doesn't always have to be Europe or the United States. It can be India also. Why not? We have very bright youngsters who are asking questions. I'm not saying don't go abroad, but take your thoughts and impose it on the system, whether this is important. So that's how we are making progress, by not necessarily agreeing with the mainstream. So it's a challenge, it's a battle because there's a lot of resistance. But we must respect our own ideas.
Absolutely, and the response you gave, I really hope this like everyone, every Indian, and I think everyone should listen to this advice and think about it seriously because uh, I personally believe like if people could think for themselves, like you said, think for yourself and break the tradition. I think that is the most important advice that possibly can be given to a young student who wants to explore the foundations of truth, if I put it that way, because uh, Indians and not just Indians, I mean, in general, today's students have a lack, in my experience, although I am not very old, but in my experience, students have a lack of this fighting against tradition and they always want to save their career first. But I think that's not how breakthroughs are made. And I mean, in a life of 70 or 80 years, what matters is we do something that matters to us, not something that is validated by society or by the system. So I sincerely hope if whoever is watching this video, please listen to sir's advice, especially this part, and try to follow along his path. So at last, I would like to ask two more questions. I think the one of the questions has already been answered by sir in his last, but still, just I would like his opinion. So, firstly, Einstein famously remarked that God does not play dice with the universe. To which some people like Niels Bohr said that stop telling God what to do. Now, fundamentally, do you think? I think you would agree that the universe could be deterministic at the very deep level. Maybe we don't know everything yet, but once we find the theory of everything or the final theory, then it would be deterministic. Or do you think like maybe there would be some amount of randomness? Now, the reason I'm saying is that in quantum mechanics there is time symmetry. Like quantum evolution, the information is preserved and everything, but at the macroscopic level, when many atoms or many particles come together to form complex systems, then we move into the domain of statistical mechanics. Then there is like this entropy and all. Then time symmetry does not hold. Some things are more likely than others. Things that in the direction of increasing entropy. So, like, what would be your views on this?
Yeah, so let's separate this into two questions. One is the underlying world deterministic, and secondly, why is the emergent macroscopic world having an arrow of time? So let's keep the second one apart from for a moment. So if the six-dimensional space-time picture is correct, we can restore locality, but we still have indeterminism. So what we call it is indeterministic locality, not local realism, but local unrealism, if you want, or local indeterminism, because that is still consistent with Bell's inequalities. At a deeper level, we take note that trace dynamics is a deterministic theory. It's not indeterministic, it is deterministic. Indeterminism arises in an apparent way from coarse graining the underlying theory, like in Brownian motion, the apparent random motion of the pollen grain is because of ignorance of the microscopic system, and the microscopic system is deterministic. Similarly, trace dynamics is a deterministic theory underlying the randomness aspect of quantum mechanics when we make a measurement. And that arises because of ignorance of the underlying theory, which is trace dynamics. The emergent theory has apparent randomness, but the underlying theory is deterministic. How that will be made consistent with Bell's inequalities, I still have to understand that. But in that sense, Bell's inequalities would also be emergent. So we can leave that for some other day. As far as the arrow of time in the macroscopic world, I think it is, to my understanding, an unsolved problem. It has to do with the initial conditions at the Big Bang, which, as Roger Penrose emphasizes, those are very special initial conditions. Matter was in a maximum entropy state, like in radiation, thermal radiation, but gravity was in a very low entropy state. The Weyl curvature was zero. The Big Bang has zero Weyl curvature. The universe is homogeneous and isotropic. And Weyl curvature seems like a measure of entropy. So the universe began in a low gravitational entropy state, and then the entropy increases and gives an arrow of time in the macroscopic world. But why did it begin in that special state? So I think that's an open question.
Yeah, and I think it has a lot to do with the initial conditions of the universe because even Boltzmann so many years back formed this idea that the universe was like the if the universe was so smooth, the early universe was so smooth. I mean, back then we didn't have theories like inflation and stuff, but Boltzmann formed this past hypothesis and stuff like the universe could be a low entropy fluctuation from a and these kind of ideas. Although this is very
Mm,
like this is really unsolved because things like Boltzmann brain and all they are more speculation. They don't have any scientific. But the point I'm trying to say is like even Boltzmann could identify the problem. So I think it has a lot to do with the initial conditions. But unfortunately, we don't know like anything definite about that. So
mm,
the last question to you, sir, would be, although you already gave some advice, but anything else you would like to say for the present generation, especially the ones who want to study physics, especially in
mm.
a country like India where physics education is not really like emphasized or encouraged even in some places. So what would you like to like anything you would like to say to
Yeah.
that generation?
I would like, say, to draw historical attention to Europe at the beginning of the 20th century. There's this unexplained or end of the 19th century Planck, this unexplained black body radiation spectrum, atomic spectra of atoms which are like hydrogen. These are not being explained by classical mechanics. Black body radiation is not being explained by classical mechanics. Michelson-Morley experiment is not explained by classical mechanics. This required a courageous break with classical physics and tradition. That requires a great deal of courage, breaking from the mainstream. Mainstream was Newton. Mainstream at the beginning of the 20th century was Newton. Then come Planck, Einstein, Niels Bohr. They break with tradition because data tells them that we need new ideas. That requires great courage to think, courage and vision to think differently from others. They were essentially loners, right? Planck, Bohr, Einstein, they were loners at the turn of the 20th century. So I would say to young Indian students who are interested in physics, go back and see what was happening at the beginning of the 20th century. Compare what's the scene today. There are analogous problems. Why is the fine structure constant 1 by 137? Why is the muon 200 times heavier than the electron? Why are galaxy rotation curves flat? These questions don't seem to be answerable by today's classical physics, which is quantum mechanics and relativity. There is again a need for break from tradition. So be Niels Bohr, be Einstein, be Planck. Think what you would do to solve the most pressing problems of today. And I would say those problems are quantitative. Don't go say I have to quantize gravity or I have to unify the forces. Say that there is this thing that is not understood. What am I supposed to do about it to make it understood? Yeah, you see what I'm saying? Yeah. And
Absolutely.
foundational problems of quantum theory. Why does the wave function collapse? Why is there the quantum non? Go for these big questions. If you try to solve them, you will make progress. You'll learn good things.
Yes, absolutely. So I would like to end this discussion with a small comment. Like, 100 years have already been, like, it's 100 years of quantum mechanics, yet we don't understand like the foundational problems. And one big thing is, as sir said, it is it has much ignored. It has been much ignored in the academic circles. Like, shut up and calculate approach has been the more dominant one. So I remember in one book I read like about Daniel Greenberger made a comment like Einstein said that if quantum mechanics was correct, then the world would be crazy because Einstein didn't accept it as a complete theory. And definitely it is not a complete theory. There are a lot of things we don't understand. In its present form, it is not a complete theory. And in response, he wrote that Einstein was right, the world is crazy. So with that, I would like to say that be crazy. Like if you want to do something, to understand the universe in a better way, make some significant contributions. Be like Einstein and be crazy. Like don't stick to the convention. That's what I would like to say, and I think sir would agree. And yeah, quantum foundations definitely deserves much more attention. And so yeah, in the end, I think it was a very insightful discussion. And once again, thank you so much for giving us so much time, sir. It was a very long and very rigorous discussion. But thank you for your time so much, sir. And
Thank you.
I'm really thankful to all of you who are watching the video. And if you have any comments, you can comment down below. And I hope you enjoyed the video. Thank you so much.
Thank you.